Hello everyone. The title of this video is Evaluate a Polynomial Using the Remainder Theorem. So every example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.5, called Zeros of Polynomial Functions, and I'm under the heading Evaluating a Polynomial Using the Remainder Theorem. Alright, and each example I'll do is either going to be an example from the reading or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Okay, so what is this remainder theorem? They kind of go through it a little bit here, and I'll talk this one out for you. So remember in section 5.4, and I put out some videos on this stuff, we did polynomial division. So suppose you divided a polynomial called f of x by a divisor called d of x. And there was a quotient, which they're calling q of x, and a remainder, which they're calling r of x, q for quotient, r for remainder. And the result of any division problem could be written this way, if you recall from the previous section, right? The dividend was equal to the divisor times the quotient plus the remainder. Well, what if the divisor was just a simple degree 1 polynomial with a lead coefficient of 1, just an x minus k? Well, if that's the case, then the d of x is replaced by x minus k, and the remainder is just going to be simply a constant. Right? That's why they say instead of r of x, they just say r, right? Just a number. Well, if that's the case, then if f of x can be expressed now as x minus k, the divisor, times some quotient q of x plus a numerical remainder r, what happens when we plug in k? Well, you see, if you plug in k for x, you'll get f of k equals k minus k. Well, that says 0, so that first term disappears, and then you got plus r, so you just end up with r on the other side. And that's what the remainder theorem basically says. The remainder theorem tells you that if you divide a polynomial f of x by x minus k, the remainder, r, is just going to be the value of that polynomial at k when x equals k. Right? F of k is just equal to r here, see? And there it is, right? See, if a polynomial f of x is divided by x minus k, then the remainder is just whatever the value of that polynomial is at k, f of k. And they go through a little how-to here. I'll leave you to read that, right? But let me show you what I mean. Well, let me show you some examples, right, from the book here. All right, so I've got them written out. So it's evaluating a polynomial using that remainder theorem. Use the remainder theorem to evaluate. So we have a polynomial. F of x equals, it's a fifth degree polynomial. 2x to the fifth minus 3x to the fourth minus 9x cubed plus 8x squared plus 2. What's the value at x equals 3? Right, so we're asked to find f of 3. All right. Now the original method would be just to plug it in, right? I'll call this the original way. Doesn't really have a name, but the original way was just plug it in and simplify. So f of 3 would be equal to 2 times 3 to the fifth minus 3 times 3 to the fourth minus 9 times 3 cubed plus 8 times 3 squared plus 2. And this can be a bit of a pain, especially with higher powers. Alright, now the fifth power isn't that high, but if the number was large, if my base was large, it would be annoying. But 3 and these aren't that bad, but still, look at this. This can get a little bit tedious here. 3 to the fifth power would be 243. Right, 81 times 3, 243 minus, and then now 3 times 3 to the fourth, this is just 3 to the fifth again, so that's 243 in total, right? I know 3 to the fourth is 81, but then times 3, so you got minus 243 there. Then minus, now here's another one where 3 to the third is 27, but then times 9, that's another 3 squared. This is another 3 to the fifth. That's another 243. All right, now here is not happening. 8 times 9. All right, 8 times 3 squared is 9. 8 times 9 is 72. Plus 2. All right, and then we get our final, but now we'll simplify. Now, see how I have two 243s here, and then I'm subtracting another two 243s, so this all makes 0, and I'm left with 72 plus 2, that's 74. All right, so f of 3 is 74. Now, this was the original way of doing things with a function, a polynomial function. Right? I say, here's a polynomial function, what's the value of 3? You just plug it in and simplify. And we ended up with 74. Well, they're asking us to use the remainder theorem. So what did that state, right? So if I want f of 3, right, by this remainder theorem, f of 3 should be equal to the remainder when dividing f of x by x minus 3. When dividing f of x by x minus 3. Right, so if you were to take this fifth degree polynomial here and divide it by x minus 3, the remainder will be what f of 3 is, right? Because again, f of x is going to be equal to x minus 3 times some quotient, q of x, right? This is the quotient, right? Which I don't know. I don't know what it is yet. I haven't done the division, but there's going to be some quotient, right? And then plus some remainder, right? Which they were calling r. I'm just writing kind of what they had in the book, right? This is the way, if you divide a polynomial by x minus 3, you should be able to do this, right? Write that polynomial as x minus 3, the divisor, times the quotient plus the remainder. And so you see that f of 3 would be equal to r, right? Because 3 minus 3 in this first term, 3 minus 3 is 0. So that's what the remainder theorem states. Now, if you remember from last section, right, section 5.4, if we're dividing, right, if the divisor is degree 1 with lead coefficient 1, which this is, it's a 1x minus 3, we can use synthetic division. I say we can use it. I mean, if you want to do lawn division, go ahead, but lawn division would probably take more writing and more thinking than I did here when I just plugged it in. Right? We can use that synthetic division, which again is in section 5.4 of this same text. Now I'm going to assume you remember my video on synthetic division, so I'm just going to jump right to it. All right. So I showed you the way I was taught with this big cross symbol. Now I'm dividing by x minus 3. The value of k was 3 then here. So I put 3 in the lower left, and then the coefficients of the polynomial we're dividing into up top. In descending order, without skipping any powers, right? So if there are any missing powers, I put a 0 for that. There's 2x to the 5th, negative 3x to the 4th, negative 9x cubed, positive 8x squared, 0x to the 1st, right? And then positive 2 for the constant, and then a little bar here separating my quotient from what we're going to be focusing on is the remainder. And remember how this goes. You drop the lead coefficient down, then you did multiply, add, multiply, add, multiply, add, multiply, add, until you got to the end. 3 times 2 is 6. 6 plus negative 3 is 3. 3 times 3 is 9. 9 plus negative 9 is 0. 3 times 0 is 0. 0 plus 8 is 8. 3 times 8 is 24. 24 plus 0 is 24. And 3 times 24 is 72. And 72 plus 2 is 74. And that's the key, right? So, I mean, from this line, again, if you remember this from last time, that means f of x is x minus 3 times, and we have the quotient here, which would be a degree 4 polynomial, right? It's in descending order. So 2x to the 4th plus 3x cubed plus no x squared plus 8x plus 24. Don't really care about that. And then you got plus 74. So, f of 3 is just, 0 plus 74, right? The remainder. That was just the remainder when you divided. And that's exactly what I got on the previous page, just plugging in the number. Right? Now, I didn't need to write all this x stuff here. I could have just said, hey, remainder theorem tells us that f of 3 is 74. And the nice thing about this is now, basically, when you're given a polynomial, you can set up the synthetic division symbol, and you basically have an input-output table, right? Input over here, and then whatever is over here is the output. Right? Whatever's in the remainder spot is the output for that input. Right? I plug in 3, I get an output of 74. Yeah, but that's what the remainder theorem states. The value of a polynomial function at some input is just the remainder when dividing that polynomial by x minus that input. Okay. And again, if you want to check it, just plug it in and see what you get. You should get the same number. See how I got 74 in both cases. So, I mean, if you're getting the same thing twice, chances are you probably did it right. Or you made the same mistake twice. But there's a good chance you probably didn't do that. Right? Yeah, so that's all we're doing. So it's basically what we're doing here is synthetic division. So if you remember synthetic division from section 5.4, you should have no problem with this. So again, use the remainder theorem to, now it says find the remainder. Alright, so this is kind of flipping it around on us. Here I have a division problem. Alright, we have x to the 4th minus 9x squared plus 14 divided by x minus 2. If I call this polynomial f of x, right, say f of x was this degree 4 polynomial here, then the remainder should be f of 2. Right, I'm dividing by x minus 2. So the remainder, when I do this division, should be the value of the dividend at x equals 2. Well, let's do this. Let's see. So let's do it both ways again. Right? Let's see what's f of 2. So I plug 2 into this numerator polynomial. The dividend is 2 to the 4th minus 9 times 2 squared plus 14. 2 to the 4th is 16. 2 squared is 4. 9 times 4 is 36. So I got minus 36. And then plus 14. 16 minus 36 is negative 20. Plus 14 is negative 6. This should be the remainder. This should be the remainder when I do this division. Well, let's see. Let's actually divide. and check it. Now I am dividing by a linear polynomial with a lead coefficient of 1, degree 1, lead coefficient 1, so I can use synthetic division. So dividing by x minus 2, so the value of k is 2. And then up top, the coefficients of the dividend, 1x to the fourth, 0x cubed, right? Don't forget your missing powers. Negative 9x squared, 0x to the first, and then the constant term is positive 14, then a little bar to separate the quotient from the remainder. And remember, the lead coefficient just gets repeated, drop down. 2 times 1 is 2, 2 plus 0 is 2, 2 times 2 is 4, 4 plus negative 9 is negative 5, 2 times negative 5 is negative 10, negative 10 plus 0 is negative 10, 2 times negative 10 is negative 20, plus 14 is negative 6. Oh my goodness. Exactly the same. All right, which we said it would be, right? We said the remainder should be the value of that numerator, the value of the dividend at x equals 2, since I was dividing by x minus 2. All right, and yeah. Right, we have from this line here, we can say that x to the fourth minus 9x squared plus 14, or what I called f of x, we could say that this is equal to x minus 2 times, and then these are the coefficients of the quotient, which would be a degree 3, x cubed plus 2x squared minus 5x minus 10, and then plus negative 6, right, minus 6. So see, if you were to plug in 2, right, so if you were to plug in 2, you see you got 2 minus 2 here. This would be nothing. And then you got minus 6 at the end, right? So it gives me the remainder. So either way, you plug in 2 to the numerator there, the dividend, you get negative 6. You actually do the division, you get a remainder of negative 6. Either way, right? They should be the same thing. That's what the remainder theorem states. All right, let's do that again. So another division problem, and I'm asked to use the remainder theorem to just, what would the remainder be, right? What would the remainder be without doing the division? So once again, if I took the dividend, or the numerator, if you want to call it that, if I called that f of x, or g of x, or whatever you want, the remainder of this division, according to that remainder theorem, should be the value of this polynomial, which I called f, at negative 1. Right? Because remember, x plus 1 is x minus negative 1. Right? This is the same thing as x minus negative 1. So the value we're talking about plugging in is negative 1. Right? Well, let's see. What is the value of that polynomial at negative 1? Right? That'd be negative 1 to the fourth plus 5 times negative 1 cubed minus 4 times negative 1 minus 17. Negative 1 to the fourth would be 1. Negative 1 to the third would be negative 1, so you got minus 5 for the second term. Negative 4 times negative 1 is positive 4, and then minus 17. So that's 1, minus 5 is negative 4, plus 4 is 0, and then you get negative 17. This should be the remainder when you divide. Now, let's see. Is it actually the remainder? Now, because the divisor, let's actually divide now and see. Because the divisor is once again a degree 1 with a lead coefficient of 1, I can go to synthetic division. All right, the value of k would be negative 1 if it's x plus 1. Coefficients of the dividend are 1x to the fourth, 5x to the third, 0x squared, negative 4x to the first, and then negative 17 for the constant. Drop the lead coefficient, multiply negative 1, you got add positive 4, multiply, you get negative 4, add, you get negative 4, multiply, you get positive 4, add, you get 0, and then multiply, you got 0, and then add these, you get negative 17, and oh look, it's exactly the same as when I just plug negative 1 into the numerator or plug negative 1 into the dividend. And again, an easy way to write another way to write this would be f of x, right? The x to the fourth plus 5x cubed minus 4x minus 17. You could rewrite it as x plus 1 times, and then the coefficients of the quotient here would be a degree 3, x cubed plus 4x squared minus 4x plus 0, no need to write plus 0, and then minus 17. And so you could see that when I plug in -1, I'd get -17 back. I'd just get the remainder. Right? -1 plus 1, this first term would be 0, and then I'd have minus 17. And that's, again, I'll say it almost every problem here, that's what the remainder theorem states. When you divide a polynomial by x minus k, the remainder will just be the value of that polynomial, the value of the dividend at k. All right, so I just got two more of these, same kind of problem. All right. So here we're dividing by x plus 6, that's x minus -6. All right, so the value of k is -6. And once again, if I call this dividend f of x, according to that remainder theorem, the remainder, when I divide these two polynomials, the remainder should be the value of this numerator, the value of this dividend at -6. All right. So let's see what that is. All right, so f at -6. That's 5 times, -6 to the 5th power minus 4 times -6 to the 4th power plus 3 times -6 to the 3rd power minus 2 times -6 squared plus -6 minus 1. Well, see how this one's going to be a little annoying, because raising 6 to the 5th power, I don't like that. All right, and I don't feel like using a calculator, so I'm just going to go right to the division, and I'll tell you what this should be equal to, and then you can use a calculator if you want to check yourself. But we're plugging in -6, right, dividing by x plus 6, so there's a -6 here. All right, so I'm going to do the division part, and I'll tell you what this should be equal to, what this polynomial at x equals -6 should be equal to. We have 5x to the 5th, -4x to the 4th, 3x cubed, -2x squared, 1x to the 1st, and then -1 for the constant term, so no zeros. Drop the 5, pardon me. Multiply, that's -30. Add, you got -34. Multiply, that'll be positive. Now 180 plus 24 is 204. Add, this might get annoying too. Maybe I will pull out a calculator. 204 plus 3 is 207. Then -6 times 207. Now 6 times 200 would be 1242, right? 7 times 6. So negative 1242. Then minus 2 plus -2 would be -1244. And yeah, alright, so let's see, 6,000. And then 6 times 200 would be 1200. 6 times 40 would be 240. And then 6 times 4, 24. Add those up, 4, 6, 4, 7, 7,464, and positive, right? 7,464 plus 1, 7,465. And then I'm going to do this. 6 times 7,000 would be 42,000. 6 times 400 would be 2,400. 6 times 60 would be 360. And then 6 times 5 is 30. And then adding these up, you got 0, 9, 7, 4, 4, 44,000, but negative 44,790, and then plus -1, negative 44,791. That's what this will be equal to. Now, yeah, the numbers got large and annoying, but I think it's better than doing 6 to the 5th and then 6 to the 4th and 6 cubed and all that, and then multiplying and adding. And you know what? Just to be honest here, let me keep myself honest. Let's go to a calculator and punch this in. All right, so go to that. I got that Desmos calculator up at desmos.com, free online graphing calculator. I'm just going to put in, f of x equals, and then that dividend, 5x to the 5th minus 4x to the 4th plus 3x cubed minus 2x squared plus x minus 1, and then just what's f of negative 6, and yeah, negative 44,791. So looks like I did okay by hand here, negative 44,791. Okay, so yeah, a little annoying because of the numbers, but you see, I think it was easier. Again, I said this earlier, but I think it's easier to do it with the synthetic division because you're just multiplying and adding and not raising to high powers. The raising the powers can be a little tedious, but if you just multiply and add every time, I mean, yeah, sometimes the numbers get a little annoying. You got to do some little extra work, but it's a lot less work to do by hand than it is to raise to a bunch of high powers, in my opinion. All right. And then I got one final example, hopefully with some smaller numbers here. So once again, we're asked to, find the remainder. What would be the remainder when you divide these two? We're dividing by x minus 3, right? A linear with a lead coefficient of 1. So that remainder theorem will apply. Right. So once again, if I call this numerator polynomial, or the dividend, f of x, then the remainder should be the value of that polynomial at x equals 3, right? I'm dividing by x minus 3. And again, it only applies when you're dividing by x minus k. All right, and what should that remainder be? Again, you can plug 3 in. Say f of 3 is 3 times, 3 cubed plus 4 times 3 squared minus 8 times 3 plus 2. And this one isn't so bad. The numbers aren't crazy. So 3 times 27, that's 81. 4 times 9 is 36. Minus 8 times 3 is 24. Plus 2. 36 minus 24 here is 12. Plus 2 would be 14. 81 plus 14 is 95. All right, so the remainder should be 95. Well, let's see. Let's actually divide one more time. I'm using x minus 3, so the value of k is 3 here. And the coefficients of the numerator, the coefficients of the dividend are 3x cubed, positive 4x squared, negative 8x to the first, and then positive 2. Drop the 3. 3 times 3 is 9. 9 plus 4 is 13. 3 times 13 is 39. Then minus 8 would be 31. And then 3 times 31 is 93. Plus 2 is, oh, look at that, hooray, 95. Right? So, I mean, it should have been the same. Right? The value of this polynomial at x equals 3, right, should have been the same as the remainder when I divided them. Right? I divided that polynomial by x minus 3, and it is. Really, the point of all these exercises is just to verify for yourself that that remainder theorem is a true statement. Right? When you divide a polynomial by x minus k, the remainder should be the value of that polynomial at x equals k, and vice versa. Right? All right, good. All right, so I'm hoping that watching me go through these, 5 examples here demonstrates the remainder theorem enough to you to where you could work on it and, work through problems involving the remainder theorem on your own. Really, you should just be able to use synthetic division. All right, you should be able to do synthetic division at this point, and that's really the major thing here. Can you perform synthetic division, and recognize when you can perform synthetic division. All right, and thank you very much for watching.